Let's start this section on project management with some basics. We define a project as a temporary and thus non-repetitive operation. Projects have a limited time frame, have one or more specific objectives, a temporary organizational structure, and thus often are operated in a more ad hoc improvised management style. We use an example to illustrate several tools and techniques of project management. This table here shows the activities that need to be done to complete our example project. A quick and rather naive view of the table is that the total time to complete the project will be 95 days when we sum all the expected duration for all the activities. Alternatively, one equally naively claimed the proposal development should take 21 days, the duration of the longest activity here. Both of these views omit an important aspect of the nature of project management. Some but not all of the activities are dependent on each other. For example, activity A3 requires the completion of activity A2. Such dependencies are also referred to as precedence relationships. They can be summarized in a dependency matrix, which is shown in this table. In the dependency matrix, each column represents an activity that provides information and each row indicates an activity that receives information. An entry in column I and row J suggests that the activity in the ith column, AI, provides information to the activity in the jth row, AJ. We also say that AI precedes AJ or that AJ is dependent of AI. Dependent activities require information or physical output from the input providing activities. The dependency matrix implicitly suggests a sequencing of the activities and thus dictates the flow of the project. The project will start with activity A1 because it does not have any input providing activities. It will end with activity A10. Similar to process flow terminology, people often refer to a preceding activity as upstream and the dependency activity as downstream. There exist multiple approaches to represent project information displayed in those two tables. In the activity on node representation, nodes correspond to project activities and arrows correspond to precedence relationships, with an arrow going from the input providing activity to the corresponding dependent activity. To create an activity on node representation of a project, we start with the activity that requires no input. In our case, that is activity A1. We then work our way through the dependency matrix, mimicking the evolution of the project. First, we create a node in the form of a box for the activity, including its name as well as its expected duration. Second, after creating the node for the activity, we consider the activity as done. Thus, all information provided by the activity to its dependent activities is now available. We can draw a line through the corresponding column and draw an arrow out of the activity for each dependency, for each X in the previous table. Next, we look for any other activities in the dependency matrix that has all its information providing activities completed and go back to step 1 until we have worked ourselves to the last activity. If we repeatedly execute these 3 steps, we obtain a graph as shown in this figure. This graph provides a practical and visual way to illustrate the evolution of the project. What matters for the completion time of the project, however, is not the individual activity times but the completion time of the entire project. The completion time requires all activities to be completed. In fact, we will see that in this project the activity with the longest duration, A7, will not constrain the duration of the overall project. So how long then will the project in this figure take? This turns out to be a tricky question. It is intuitive that the project can be carried out in less than 95 days, the sum of the activity times. Some activities can be carried out in parallel, and so the 10 activities do not create a 10-person relay race. On the other hand, the degree to which we can execute the activities in parallel is limited by the dependency matrix. For example, activity A3 requires the completion of activity A2, which in turn requires the completion of activity A1. Things get even more convoluted as we consider activity A7. For it to be completed, A3 and A6 have to be completed. A3 in turn requires completion of A2 and A1, while A6 requires completion of A4, which once again requires completion of A2 and A1. To correctly compute the completion time of the project, a more structured approach is needed. This approach is based on considering all possible paths through the network in this figure. A path is a sequence of nodes, activities, and directional arrows. For example, the sequence A1, A2, A3, A7, and A10 is a path. Every path can be assigned a duration by simply adding up the durations of the activities that constitute the path. The duration of the path A1, A2, A3, A7, A10 is 49 days, the sum of the duration of all those activities. The number of paths through the AON representation depends on the shape of the dependency matrix. In the easiest case, every activity would just have one information providing activity and one dependent activity. In such a project, the dependency matrix had just one entry per row and one entry per column. The duration of the project would be the sum of the activity times. Every time one activity provides information to multiple activities, the number of paths is increased. In this project here, and the graph shown here, we can identify the following paths connecting the first activity A1 with the last activity A10. This is the first one, A1, 2, 3, 7, and 10, 49 days. Next, A1, 2, 3, 8, 9, and 10 with duration of 53 days. This is next one with duration of 51 days. This is next, 55 days. And this is the last activity, duration 57 days. The path with the longest duration is called the critical path. Its duration determines the duration of the overall project. In our case, the critical path is A1, A2, A4, 5, A8, 9, and 10, and the resulting project duration is 57 days. Note that A7, the activity with the longest duration, is not on the critical path. The exercise of identifying every possible path through the project graph along with its duration is a rather tedious exercise. The more activities and the more dependency relationships we have, the greater the number of paths we have to evaluate before we find the one we truly care about, the critical path. Fortunately, there is a simpler way to compute the project duration. The idea behind the easier way is to compute the earliest possible start time for each activity. For each activity, we can find the earliest start time. By looking at the earliest time, all information providing activities have been completed. The earliest start time of the first activity is time 0. The earliest completion time of an activity is the earliest start time plus the activity duration. We then work our way through the project graph, activity by activity, starting from the first activity and going all the way to the last. More formally, we can define an algorithm to compute the earliest completion time of the project. The approach is similar to our method of coming up with a graphical representation of the project graph. First, we start with the activity that has no information providing activity and label that activity as the start. The earliest start time of that activity is defined as 0. In this case, this is activity A1. The earliest completion time is the duration of this activity. Second step, identify all activities that can be initiated at this point, that have all information providing activities complete. For a given such activity, I compute the earliest start time, as earliest start time for AI is the maximum of earliest completion time of AG, where AG are all activities providing input to AI. You can see this and duration of A7, A8. Compute the earliest completion time of AI as earliest completion time of AI equals earliest start time of AI plus duration of AI. Consider activity I is completed and identify any further activities that now can be initiated and go back to step 2. And for this project, we will get this table. For activities, their earliest start times calculations, duration, and earliest completion time. This table is created from the top to the bottom, one activity at a time. As you construct a given row I, you have to ask yourself, what activities provide information to I? What activities does I depend on? You can see this by reading row I in the dependency matrix, or you can see this in the project graph. Based on the earliest start and earliest completion time, we can create a Gantt chart for the project. The Gantt chart is basically a timeline with the activities included as bars. Gantt charts are probably the most commonly used visualization for project timelines. Note that unlike the activity on node representation, the Gantt chart itself does not capture the dependencies of the activities. Based on the previously explained computations of the earliest start and completion times, we have already ensured that activities only get initiated when all required information is available. The Gantt chart, a simple Gantt chart for this project, is shown in this figure. We have used the Microsoft project tools. Let's continue with the slack time. It lies in the nature of the critical path that any delay in activities on the critical path will immediately cause a delay in the overall project. For example, a one-day delay in activity A9 will automatically delay the overall project by 1 day. However, this is not true for activities that are not part of the critical path. We can delay activity A7 even by several days without affecting the overall completion time of the project. In other words, activity A7 has some built-in wiggle room. The technical term for this wiggle room is slack time. It is the amount of time an activity can be delayed without affecting the overall completion time of the project. The slack time of an activity is determined based on an additional set of calculations known as the late start schedule. So far we have computed the earliest start time and earliest completion time of each activity by going through the project from beginning to end. We now compute the latest start time and latest completion time for each activity such that the project still completes on time. We do this by beginning with the last activity and working our way backward through the project until we reach the beginning. Thus we start with the last activity A10 and end with the first activity A1. So let's start with the last activity. Assuming we want to complete the project as early as possible, we define the latest completion time of the last activity as being the same as its earliest completion time. In this case, 57. There exist some cases in which an early completion is not desired. Instead, there exists a target time at which the project should be complete. In this case, we can define the latest completion time of the last activity as the target date. The latest start time of the last activity is simply the latest completion time minus the duration of the last activity. In this case, 57 minus 5 equals 52. More generally, we define the latest completion time for an activity as the smallest, earliest, latest start time value of all activities that are depending on it, and the latest start time as the latest completion time minus the duration. Consider activity A9, which only has A10 as dependent activity. Thus, we can define that the latest completion time of A9 equals latest start time of A10, which is 52. And then latest start time of A9 equals latest completion time of A9 minus duration A9, which is 52 minus 15, 37. In the same manner, we can compute the latest start time of A8, 27, then A7, 31. Note the difference between the earliest start time of A7, which was 95, and the latest start time of A7, which we just found to be 31. In other words, we can delay the start of A7 by 6 days without affecting the overall completion time of the project. Based on this observation, we define the slack of an activity as slack time equals latest start time minus earliest start time. In the same way, we can compute the other information of the late schedule. Note that the columns latest start time and latest completion time are computed by going backward through the project graph. Thus, we start with the rows at the bottom of the table and work our way up. As expected, the slack time of all activities on the critical path is 0. What is the benefit of knowing how much slack time there is associated with an activity? The main benefits from knowing the slack time information are two. Potentially delay the start of the activity, to the extent that we can delay the start of an activity without delaying the overall project. We might prefer a later start over an earlier start. Because activities are often associated with direct expenses, simple discounted cash flow calculations suggest that the start times be delayed wherever possible. Accommodate the availability of resources. Internal or external resources might not always be available when we need them. Slack time provides us with a way to adjust our schedule, as shown in the Gantt chart, without compromising the completion time of the overall project. Based on this information, we can augment the initial project graph and present all information we computed for each activity in a graphical format. This representation, shown in this picture, is the output of many commercial software packages dealing with project management as well as a set of consulting tools. Note that all of these computations assume that there exists no uncertainty in the activity durations and dependencies. Uncertainty is a subject of the next lecture. Given our definition of projects as temporary operations that deal with non-routine work, projects often face a significant amount of uncertainty at their outset. Incorporating this uncertainty into the project plan is a central concern of project management. How much uncertainty a project is exposed to depends on the nature of a project and its environment. Launching a new entrepreneurial venture is likely to be associated with more uncertainty than the construction of a residential building. We find it helpful to distinguish among 4 project management frameworks that will present in increasing order of the level of uncertainty. First one, random activity times. So far, we have behaved as if all activity times in the project were deterministic. They could be predicted with certainty. However, it lies in the nature of many project activities that the duration can vary considerably. Often, project managers are asked to come up with a base case, an expected case, and a worst case scenario for the duration of each activity. With that information in mind, it is possible to compute the variance of an activity time as well as the probability of meeting a certain due date. This figure here shows the activity durations for a sample of cardiac surgeries in the operating room of a large hospital. We observe that there exists a considerable amount of procedure variations. Moreover, we observe that the distribution is not symmetric. Activity durations that are more than double the mean duration can happen. The distribution has a long tail. When facing uncertainty in the activity time durations, it is important to understand that uncertainty in the activity duration is a bad thing because it, on average, will lead to a later completion time of the project. It is a misconception that uncertainties in activity times will cancel each other out. When some activities are completed early and others are completed late, the overall impact on the project duration is almost always undesirable. To see this, consider the simple project graph displayed in this figure. On the left side on the figure, we have a project with deterministic activities. Given the activity durations of 5 days for A1, 4 days for A2, and 6 days for A3, as well as the dependency structure shown by the project graph, The critical path of this project is A1, A3, and the completion time is 11. Now consider the activity times on the bottom of the figure. A1 now has a completion time of 3 days with a 50% probability and 7 days with a 50% probability, and A2 has a completion time of 2 days with a 50% probability and 6 days with a 50% probability. Note that in expectation, on average, the completion times of A1 and A2 have not changed, but the expected completion time of the project has. To see this, consider the calculations in this table. Observe that the expected completion time is 11.75 days. Almost 1 day, to be exact, longer than in the deterministic base case. Note that this relies on a rather optimistic assumption, in this case, that both activities are completed early. We implicitly assume that A3 has the flexibility of starting earlier than planned when both A1 and A2 are completed early. If we cannot benefit from the early completion of activities, the overall penalty we incur from uncertainty would be even higher. In the first 3 scenarios, we are slower than the deterministic completion time of 11 days. Only in the last case are we faster. Thus, we are not just exposed to the risk of the project running later than in the deterministic case, but will be running later on average. The reason for this effect is that the critical path of the project can potentially shift. In other words, an activity not on the critical path might delay the overall project because of a longer than expected duration. While A2 was not on the critical path in the deterministic base case, we saw that it was holding up the project and thus was on the critical path in the second scenario analyzed here. Next type of uncertainty are potential iteration and rework loops. The previously introduced dependency matrix in Lecture 1 had an important property. All dependencies were on the lower left of the diagonal. In other words, there existed a one-way path from the beginning of the project to the end. In practice, however, projects often require iteration. In fact, the previously discussed project commonly, in about 3 out of 10 cases, iterates between activities A4 and A9. Such iterations are typical for product development and innovation projects, where problem solving can be a more organic, iterative process. It is often referred to as rework. In general, such rework loops are more likely to happen in high uncertainty environments. For example, a development team for an internet platform might want to adjust its business plan after having launched a beta prototype, creating a rework loop. In contrast, we hope that the architect in charge of a major construction project does not want to revisit her drawings after the first tenants moved into the building. Consequently, project planning tools such as Gantt charts and the critical path method are more valuable for low uncertainty projects, and they can provide a false sense of planning accuracy when applied in high uncertainty environments. Decision trees, milestones, and exit options. The previous 2 types of uncertainty reflected the question, when will the project be completed? Activities might take a little longer, uncertain activity times, or sometimes might even have to be repeated in the rework loops, but in the end, we always complete the project. Often, however, a more fundamental question is of essence to the project manager. Will we complete this project at all, or should we terminate the project? Such uncertainty is common in many innovation settings, include venture capital funded projects or pharmaceutical research and development. For example, only a small fraction of R&D projects that enter phase 1 clinical trials will be launched in the market. More than 80% of the project will be cancelled along the way. Project management techniques, as reviewed earlier, are appropriate for handling this type of uncertainty. The threat of terminating the project because of new market data, market uncertainty, or new technical data, technological uncertainty, looms so large that it trumps the previously discussed types of uncertainty. Decision trees map out the potential scenarios that can occur once the uncertainty is resolved and the potential set of actions that can be taken in each scenario. A key insight that can be derived from such models is the observation that it is often substantially cheaper to exit a project early instead of letting costs escalate and then exiting the project later on at higher costs. The project management implication of this is that it is very desirable to move activities that resolve this type of uncertainty, feasibility studies and market research, to the early part of the project. Unknown unknowns. When Columbus set out to find a new way to sail to India, he most likely did not set up a project plan. Even for modern time explorers, be it in sailing or in business, there exist situations where the amount of uncertainty we face is simply too large to make any careful planning process meaningful. In such settings, we face so much uncertainty that we don't even know what we don't know. We face unknown unknowns. It lies in the nature of many high uncertainty projects that they will not be completed. In that sense, a timely abandonment often is the goal, as it avoids an escalation in costs. Often a useful exercise is to simply list all variables in the project that are currently not known and to look for activities that would help resolve these unknowns. At any moment in time, the project manager should then attempt to spend as little as possible to learn enough to decide whether or not to move forward with the project. This technique, also referred to as discovery-driven planning, will help resolve some uncertainties and potentially identify new ones. Project managers typically pursue a combination of three objectives: project completion time, project cost or budget, and the quality of the accomplished work. Sometimes these objectives are in conflict with one another. This then creates a trade-off among the three dimensions. Beyond trading off one goal against another goal, we can also try to break the trade-off and just be smarter about how we manage the project. The following provides a set of inexpensive actions a project manager can take to accelerate the completion time of the project without necessarily sacrificing the quality of the accomplished work or the project budget. Start the project early. The last day before the project's due date is typically a day of stress and busyness. In contrast, the first day of the project is typically characterized by little action. This effect is similar to the term paper syndrome, well familiar to most students. It reflects human optimism and overconfidence in the ability to complete work in the future. At the risk of stating the obvious, a day at the beginning of the project is equally long as a day at the end of the project. Why do little or no work on the former and jam all the work into the latter? Manage the project scope. One of the most common causes of delay in project is that the amount of work that is part of the project changes over the course of the project. Features are added and engineering change orders requested. If such changes occur late in the project, they often cause significant project delays and budget overruns for a relatively little increased quality. For this reason, it is advisable to finalize the scope of the project early on. Crash activities. Often an increase in spending allows for a faster completion time of a project. Contractors are willing to work overtime for a premium, and expensive equipment might help further shorten activity duration. However, the reverse is not always true. Projects that take excessively long are not necessarily cheaper. Because typically there are some fixed costs associated with a project then drags on forever might actually be also very expensive. Overlap critical path activities. A central assumption underlying the dependency matrix has been that an activity that is dependent on an information providing activity needs to wait until that activity is completed. However, it is often possible to allow the dependent activity to start early, relying on preliminary information from the information providing activity. For example, it seems plausible that the activity building design should be completed before starting activity building construction. However, does this imply that all of the design has to be completed? Or maybe would it be possible to begin digging the foundation of a building while the designers are still finalizing the shape of the windows? By identifying the exact dependencies among activities, it is often possible to provide the dependent activity with a head start.